Welcome to the Usefulati. Our mission is to spread the written work of the world's most useful doers in a listenable format that lets you zone in to the cutting edge. Our doer today is Casey Handmer, CEO of Terraform Industries and an alumnus of NASA's Jet Propulsion Laboratory. His company is creating natural gas out of water, sunlight, and air. You can read more about Casey and his company in the description. Now let's hear what he has to say.
Part of the series on space topics, a follow-up to my blog on atmospheres and terraforming 2018, and how to terraform Mars with cheap solar sails 2022. Unrelated, officially, from my work at Terraform Industries, where we're making cheap synthetic natural gas from sunlight and air. Somewhat related to my simulated terraformed Mars project. Download the latest super overlay here, 11 gigabytes. A new paper by Samaneh Ansari, Edwin Kite, Ramses Ramirez, Liam Steele, and Houman Mohseni describes a new low-cost method to significantly warm Mars' climate. Their method proposes tiny conductive nano antennas, each roughly 9 microns long and no wider than 150 nanometers. This structure, which is tuned for the wavelengths corresponding to thermal emission, forms a greenhouse effect greater than 5,000 times stronger than the strongest greenhouse gases known to science, the perfluorocarbons. They also do not require the construction of enormous automated fluorite mines on Mars, a planet that has no known fluorite deposits, though they probably exist somewhere. Even better, they could be mass-produced on Earth and delivered by thousands of starships. How many do we need? Roughly 1 litre per second per Kelvin degree of temperature increase. For the 30 Kelvin, we need to unfreeze the hydrosphere. That's 30 litres per second, which is about 1 million tonnes per Earth year. This assumes no help from induced carbon dioxide outgassing. 1 million tonnes per year is a lot to deliver, even considering that the Starship does not have to perform a soft landing, just disperse nano antennas into the atmosphere. The entire Mars base will require on the order of 1 million tonnes of soft-landed cargo to achieve self-sufficiency. We're talking perhaps 5,000 starships per year, each on a trans-Mars trajectory requiring orbital refilling. At $60 million per flight, that's $300 billion per year. This seems like a lot, but in the massive rapid-induced planetary global warming game, it's a bargain. If we have a city on the surface, we can likely produce nano antennas on Mars. Certainly, they're much easier to make than $100 solar sail spacecraft. The only other method that's comparable in cost is solar sails, mass-produced on Earth and launched into low Earth orbit as described in this earlier blog. Here I estimated we'd need 750 million solar sails per degree of temperature increase, each 1,000 square metres and, in their most refined form, based on cell phone technology at comparable mass, 250 grams, and cost $100 per unit. Reflect Orbital's concept is similar, and if they can achieve this price point, they could easily self-fund the terraforming effort. So 30 degrees of heating requires 22 billion solar cells over 10 years, numbers comparable in volume to the cell phone industry. These would need roughly 5,000 Starship launches. But unlike the nano antennas, they launch only to low Earth orbit and do not have to wait for a launch window, so overall launch costs could be 10 times lower. There's no reason not to do both, or even all of the above, with resources allocated to the relative merits of each terraforming method. Nano antennas are easier to make and deploy at scale. Solar sails are probably slightly cheaper once they achieve the necessary economies of scale. Additionally, billions of solar sails orbiting Mars and/or lurking in Sun-Mars L2 would look awesome. Solar sails are also relatively benign for the Mars environment. Perfluorocarbon gases involve the generation of per- and polyfluoroalkyl substances chemicals on the surface of Mars, while nano antennas have essentially identical structure to asbestos fibres, and will likely cause similar health problems if inhaled, and there will be multiple antennas in each cubic centimetre of Mars air. No one on Mars will be breathing the air anytime soon, but contamination control for human explorers may be challenging unless we can find a way to inactivate the particles as soon as they settle to a solid surface. The prospect of being able to restart the Mars hydrosphere with zero Mars surface infrastructure and total investments of low tens of billions per year is captivating. $24 billion per year pays off all of NASA. Another 24 billion could warm Mars to the point where it has rivers, lakes, and oceans, and can support primitive plant life. We should do this.